Welcome to Study Loop.
This is chapter 37, problem number 34. We're asked to calculate how much work needs to be done to accelerate a particle of mass from rest in part A. So we're calculating the work done, right? But the initial velocity is going to be 0 in part A because it says from rest to a final velocity of 0.09, 9% of the speed of light, right? So in order to calculate the work, we know that work equals to the change in kinetic energy. So in this case, we need to calculate the kinetic energy that corresponds to initial speed of 0 and the final speed of 0.09 c. So then, okay, final kinetic energy minus initial kinetic energy is going to give us some delta k. So let's write what initial kinetic energy would be. Of course, relativistic, right? So initial gamma minus 1 m c squared is going to be our initial kinetic energy. Our final kinetic energy is going to be gamma final minus 1 mc squared, right? So if we plug everything, these two, in the work equation, we're going to have gamma final minus 1 mc squared minus gamma initial minus 1 mc squared. So we have mc squareds in both terms. So let's group the coefficients of these guys. So final minus 1 minus initial minus 1, right? So if we do this, then we're going to get final minus gamma initial minus 1 plus 1, right? These are going to cancel. So as a final expression, we have mc squared final gamma minus initial gamma for the change in kinetic energy that corresponds to work. Now, in order to calculate the final and initial gamma factors, we're going to have to plug in for them, right? Which is the gamma factor is given as, this is the general formula, 1 minus whatever the corresponding velocity of that particle is over square of the speed of light, right? So we're going to write this for final gamma factor, and we're going to write it for initial gamma factor that corresponds to these two velocities. Now, let's go on a new page. Then work done equals delta k. We said that equals final minus initial times mc squared. Final is going to be 1 minus v final squared over c squared minus 1 over square root of 1 minus v initial squared over c squared. So times mc squared. Now, as you can see here, since the initial velocity is 0, this term is 0. So you're left with square root of 1 here. Square root of 1 gives you 1. 1 over 1 gives you 1. So this entire term actually equals to 1, right? So when that's the case, let's plug in the v final for here. In the first term, final for the first was 0.09 c squared over c squared minus 1 then is going to give us mc squared. So for m, we're not plugging in m or c. We're asked to leave everything in terms of mc squared. So all we need to figure out is this coefficient. If you plug everything in here, c squareds are going to cancel. As you know, if you do the algebra, then what we're going to have here is mc squared times 4.07 times 10 to the power of negative 3, right? That's what it would be the answer to part A. Now, in part B, still we're asked to calculate the work that is required, but this time initial and final velocities are different. The values are different. We're at a higher, we have much greater velocities. So again, the work done, delta k, we said that equals the final minus initial gamma factors, mc squared. Now our final velocity is 0.99 times the speed of light. The initial would be 0.9. These are given in the problem. Then what we need to do is to calculate actually this coefficient here, 1 over square root of 1 minus 0.99 times c squared over c squared minus 1 over square root of 1 minus 0.9 c squared over c squared times mc squared. So then this coefficient is going to be equal to 4.79 times mc squared. So in part C, we're asked to compare our answers to part A and B. Obviously, if we go back to the answer to part A, you're going to see that the coefficient is much smaller. So the answer to part A, answer to part B is much larger than the answer to part A. The reason for that is the greater the velocity that you want to accelerate the particle to, more energy it requires, right? And finally, if you're getting really, really close to the speed of light, actually you require infinite amount of energy. So it makes sense.